finals.
Yeah, I don't expect.
I'm Dave Meyer.
Hi.
We were on a grant proposal together.
Oh, I see. Nice to meet you. Together at my. Okay. Oh, so I don't have to introduce myself. Okay. Sure.
All ready?
Yeah, so.
So good afternoon and welcome to the Center for Transportation Studies Friday Transportation Seminar, the last one of winter term. And I'm pleased to introduce Dr. Sue An from the Department of Civil and Environmental Engineering here at PSU. She's a postdoctoral research associate. She received her bachelor's in civil engineering from Ohio State University and her master's and PhD from UC Berkeley. Her PhD just last fall. So we're very pleased to have Sue here discussing her research with us.
Okay, thank you. Thanks all for coming. So today I'm going to be presenting the work that I've done for my dissertation research, which is concerning formation and spatial evolution of traffic oscillations. Traffic oscillations are so-called stop-and-go driving motions in congested traffic. So in this study, I studied how oscillations originate in the first place and how they propagate over space. And I found some compelling evidence that lane-changing maneuvers and ramp inflows and probably outflows play significant roles. So why do we care about how oscillations evolve over space? Oscillations are a long-standing puzzling phenomenon to researchers. Researchers have theorized oscillations for decades, but there have been lack of empirical studies because they require field data with high level of detail. So consequently, what initiates oscillations and what makes them grow or diminish over space remained an open question. In fact, there seem to be two rather contradicting views. The mainstream thought on this issue is related to car following theories, which claim that instabilities in car following cause oscillations to form and grow over space. But some researchers found new empirical evidence that lane-changing maneuvers are actually linked to oscillations. But the causal relationship was not clear because the lack of detail in their data. And understanding oscillations has some important implications. It will provide a right direction in developing better models for oscillations and traffic flow in general, and better estimation models for externalities associated with stop-and-go driving, such as fuel consumptions, engine emissions, and etc., and control schemes to smooth oscillations to reduce these externalities, which will be of some benefit. So let me revisit the two contradicting views. And as I mentioned, the predominant thought is based on car following theories. These models started around 1950s, and they model how drivers follow their lead vehicles in queue. And there are many types of car following models, but here I'm showing perhaps the most well-known group, which is called Gezes, Herman, Rothery models. So these were developed by General Motors researchers back in 1950s, and they attempted to describe car following behavior as a stimulus response type of driving behavior. So stimulus being the relative speed or spacing with the lead vehicle, and response being the follower's acceleration or speed. So the basic framework was provided by Chandler et al., and it went through a series of modifications to reflect more realistic driving behavior and to match real-world observations. So the general formulation looks something like this. So acceleration of vehicle N at time t is a function of, let's see if I can do this. So function of driver sensitivity and the relative speed with her leader perceived capital T time earlier. So here capital T is driver reaction time. And driver sensitivity is a function of driver speed and relative spacing with the leader perceived capital T time earlier. And C, M, and L are scaling constants to be determined. So since the development of this model, a lot of efforts were concentrated on calibrating these scaling constants, as you can see as recent as 1993. So in the stability analysis, it was shown that oscillations formed and grew when driver reaction time was too large and caused driver overreaction as a result. And there are some empirical studies that seem to support the idea that car following has something to do with oscillations. So these are some examples. So they studied traffic without lane-changing maneuvers, either because it was a single-lane facility or lane changing was prohibited. And they observed that oscillations initiated and grew without lane-changing maneuvers, indicating that oscillations are a car-following phenomenon. But they didn't really show the mechanism of how car following triggered oscillation formation or growth. But in recent empirical studies, Kerner and Webborn, Malk and Cassidy studied multi-lane traffic with frequent lane changing on German Autobahn and Canadian freeway. And they observed that oscillations tended to form and grow near freeway interchanges where many systematic lane changing maneuvers occurred. And this indicated that oscillations in multi-lane traffic are a vehicle lane changing phenomenon. But the causality was not clear because they used loop detector data, and these were too coarse to confirm any detailed relationship. If you're not familiar with loop detectors, these are traffic sensors embedded in freeway every mile or so, and they detect vehicle passages over time, and they either measure or estimate vehicle speeds. So in my study, I also used loop detector data to observe some general features of oscillation formation and growth. But for more intricate study, vehicle trajectories were constructed from video, and these were much more suitable to study the impact of vehicle lane changing or car following. And also using video, I was able to study the effect of ramp inflows. So one of the key findings from this study is that in multi-lane freeway, oscillations form and grow by lane changing rather than car following. And car following did play a role, but it was secondary to lane changing effect. And the mechanism was such that vehicle insertion into a relatively small spacing initiates or exacerbates a decelerated state. And once a decelerated state was initiated or exacerbated, it sometimes became amplified because of car following effect. But the car following effect occurred on the heels of lane changing maneuvers, and that's why I say that car following played a secondary role. And another key finding from this study is that apart from the lane changing effect, on-ramp inflows on a congested merge dampen oscillations. And I developed a simple theory to explain this. And the theory predicts the reduction of oscillation amplitude quite well. And the theory also predicts that off-ramp outflows would amplify oscillations. And I am in the process of validating that part of the theory. So here's the outline of the rest of my talk today. So for the next 5 minutes or so, I want to provide more detailed discussion of what oscillations are. Then I want to spend some time showing you macro level features that I observed from loop detector data. Then I'll move on to micro level features that I observed from video, especially in relation to lane changing maneuvers on oscillation formation and growth. And finally, I'll discuss the effects of freeway ramp inflows and outflows, starting with the proposed theory and some supporting empirical evidence obtained in this regard. So let me start with a further definition of oscillations. So these are some relevant traffic parameters. If you know these already, please bear with me for a minute. So flow is number of vehicles per unit time observed at a particular location. And density is number of vehicles per unit distance observed at instant time. And space mean speed is average speed of vehicles observed over space and instant time. And the relationship among these parameters is such that flow is equal to density times the space mean speed. And there is a growing body of evidence that traffic behaves on average as predicted by a simple hydrodynamic theory. So the key assumption of this theory is that there's a well-defined relationship between flow and density, like the blue piecewise line shown here. So the left portion of the curve represents uncongested state, uncongested regime, so that the increase in density is accompanied by the increase in flow. And the right portion of the curve represents congested regime, so that flow becomes more restrictive when the density increases. And Q sub max, that is the maximum flow that can be achieved. And K sub jam is density when the traffic is jammed or completely stopped. At any point on this curve represents a stationary traffic state, like point A, which is characterized by certain levels of flow and density. And the average vehicle speed in the state is shown by the slope of the line that connects the origin and the state. So these are vehicle trajectories with such characteristics in flow, density, and speed. And when traffic changes from one state to another, like from A to B, the interface that divides the two states propagates as a kinematic wave at the speed equal to w. So in this case, which is the slope of the line that connects the two states. So in this case, the wave propagates upstream against the traffic since the slope is negative. So you can look at it as brake lights propagating from one vehicle to another in the upstream direction in Q. And the number of vehicles that the wave crosses within a segment is the jam density times the length of the segment as described by Newell. And I use this property to detect formation and growth in a systematic way. Then oscillations are a cyclic pattern of changes from more to less congested states. So in this case, state go is less congested than state slow. You see higher vehicle speed in state go. And you see that when speed decreases, flow decreases. And when speed increases, flow increases as well. And the change in states propagates upstream at the speed equal to w. Again, the wave propagates backward since the slope is negative. And I say that oscillations grow if the change in flow or speed becomes larger as the wave propagates upstream. And I measure the amplitude of oscillations with respect to the longer run average flow or speed to account for the changes in average state. So that concludes the further definition of oscillations. So now let me show you some macro level features that I observed from loop detector data. But before I do that, I'm going to go over the site and methods that I used to unveil these features. So here's the freeway site that I used for this study. This is Interstate 80 near San Francisco, California. This is one of the most heavily traveled freeways in the region. So the top portion is I-80 westbound going into the city, and the bottom one is I-80 eastbound. And both directions are queued during each afternoon rush because of bottlenecks located further downstream. So these blue shadings represent queues. And these yellow circles indicate loop detectors, which produce vehicle counts and speeds. And there are 8 detector stations in this freeway section. So using the vehicle counts or speeds, in this case speeds, I constructed cumulative speed curve in such a way that the slope of the curve is speed. And to predict the longer run average speed, I constructed 5-minute moving averages. And to view oscillations, I plotted the deviations of actual cumulative speeds from the moving averages and obtained a deviation curve. So by the way, these are all real data. So in each deviation curve, positive slope represents go period, and negative slope represents slow period. And the root mean squared error computed over the period of analysis measures the overall amplitude of oscillations. And these are deviation curves plotted for all 8 loop detector stations on I-80 westbound. So there are 4 curves in each detector stations, 1 for each lane. So in this figure, direction of traffic is upward, and oscillations propagate in the opposite direction. And loop station 8, which is the most downstream detector station, is located about 1 kilometer upstream of the bottleneck. So this entire section of the freeway was congested, and these were constructed on one of those days. So you see that some oscillations had already formed by the time they reached station 8, indicating that oscillations tend to form within a short distance from the bottleneck. And you also see that these oscillations propagated upstream at a nearly constant speed, even though traffic conditions change because of ramp inflows and outflows. And this indicates that the congested branch of flow density relationship is linear. And these are root mean squared errors computed for each detector station. So these are averages over all lanes. So you see that oscillations grew in general, except at station 3, as oscillations propagated upstream. At station 3, this reduction in amplitude is explained by the theory I'm proposing. But the point here is that oscillations tend to form near the bottleneck, and they grow in general as they propagate upstream. And if you look at root mean squared errors for individual lanes, then you see another interesting feature. So here I'm showing 2 center lanes as an example. You see that the 2 lanes exhibit different amplitude of oscillations, as you can see by the separation between the 2 curves. And you also see that the 2 lanes exhibit different magnitude of growth. And this is evident from stations 2 to 1. You see that oscillations actually diminished in one lane while they grew in the other. So this tells me that oscillation growth must occur on an individual lane basis. And finally, if you look at these deviation curves again, speed deviations in individual lanes were not so synchronized closer to the bottleneck, but then they are very well synchronized in the upstream locations. And this figure shows this feature in detail. So this figure was constructed by computing correlation of speed deviations between 2 neighboring lanes. And I did this for all pairs of neighboring lanes. And each point on this curve is the average of those pairwise correlations. So you see that the average correlation was relatively low, closer to the bottleneck, and it increased to about 0.9 when oscillations propagated to station 6. And this tells me that oscillations began to form in individual lanes, and they became synchronized as they propagated upstream. So based on these macro-level features, that oscillations tend to form near a bottleneck, and that oscillations form and grow in individual lanes, I looked at micro-level features by analyzing trip times and trajectories of individual vehicles in each lane to uncover the mechanisms of oscillation formation and growth. So having said that, let me move on to micro-level features that I observed from video. So to study this, I obtained vehicle trajectories from I-80 where videos were available. So this area shaded in pink is the video coverage area where that was good enough to extract vehicle trajectories. And to detect formation and growth in a systematic way, I used vehicle trip times measured in multiple contiguous segments. So here are criteria to capture formation. So this is I-80 westbound near the bottleneck, and these are 2 segments where I extracted vehicle trajectories from. So the plot on this on the right is vehicle trip time versus vehicle number. And these yellow circles, those are vehicle trip times measured in the upstream segment. And the blue squares are trip times of the same set of vehicles measured in the downstream segment. And the vehicles were numbered in the order of their arrivals to the most upstream location X0. And these solid curves are moving averages of 5 vehicles, which reveal the trends a little better. So to detect a formation, I looked for increase in trip time that was larger than 1.5 seconds. I used 1.5 seconds to exclude increase in trip times due to random fluctuations. Then I checked that there was no such increase in the downstream segment within 12 preceding vehicles. So why 12 vehicles? So that's the number of vehicles that a deceleration wave would have crossed in the downstream segment if an oscillations formed somewhere further downstream. So based on the two criteria, 5 instances of oscillations were detected, and I observed that lane-changing maneuvers trigger these formations. I'm just going to show you one example here, but other cases are included in my dissertation. So going back to this example to see the mechanism, so you see this large increase in trip time for vehicle 129, and the trip time continue to increase for the vehicles with higher arrival numbers. So I plotted trajectories around those vehicles. So this dark trajectory is for vehicle 129, and the pink one is for the vehicle that inserted itself in front of vehicle 129. So this dark circle represent what marks the time and location of insertion. So you see that vehicle 129 decelerated right after the insertion and accelerated once she presumably gained safe enough spacing. And you also see some car following effect, so that this initial decelerated state was further amplified without lane changing. But the point here is that this car following effect occurred on the heels of this vehicle insertion. And it is probably intuitive to you that not all insertions would trigger decelerated states. So I looked at the distributions of insertion spacings for 2 groups. So the blue bars are for the 4 insertions that triggered formations, and purple bars are for all other insertions. And you see that the ones that triggered formations tended to occur in smaller spacing compared to other insertions. So let me move on to growth. So as I mentioned, I studied growth in the eastbound direction primarily. So these are criteria to detect instances of growth. So this is I-80 eastbound, and these are 2 segments where several instances of growth were detected. Like the formation case, these yellow circles are trip times measured in the upstream segment, and blue squares are trip times measured in the downstream segment. And to detect growth, I looked for increases in trip times larger than 1.5 seconds in both segments, indicating that the deceleration wave crossed both segments. And I checked that these increases occurred with a lag in vehicle number of 14. So in this case, 14 is the number of vehicles that the deceleration would have crossed in the downstream segment. And I analyzed all cases of growth whose rates were larger than 5 kilometers per hour per kilometer. So this threshold represents that by the time deceleration wave traveled 1 kilometer upstream, the speed would drop further by 5 kilometers per hour, which is quite gradual. So based on these criteria, 11 instances of growth were detected. And just like formation, these were triggered by lane-changing maneuvers. And going back to this example to see the mechanism, so you see this huge growth in trip time for vehicle 439, and these are trajectories around that vehicle. So it's pretty obvious that this decelerated state was further amplified by the two insertions that occurred in front of vehicle 439. And these are distributions of insertion spacings for two groups. So the blue bars are for the insertions that triggered growth. So there were 8 of them, actually. And then these purple bars are for all other insertions. And you see that the ones that trigger growth tended to occur in smaller spacing, although it doesn't look as striking as the formation case. So before I move on, let me make a quick point. So it may be intuitive to you or even obvious to you that car following has something, lane changing has something to do with oscillations. But I want you to remember that oscillations were believed to be strictly a car following phenomenon. And my data show that car following did not instigate oscillation formation or growth. And oscillation formation and growth were always linked to vehicle lane changing maneuvers. And car following was involved, but as a secondary effect to lane changing. So I hope that point was clear. And let me move on to the final item of today's presentation, effects of freeway inflows and outflows. To motivate this discussion, these are deviation curves constructed for eastbound direction. So these are deviations in flow aggregated over all lanes instead of speeds. So here I'm working with flow because the theory was developed based on the concept of flow conservation. But you see that oscillations propagated at a nearly constant speed, and they grew in general as they propagated upstream. And these are root mean squared errors computed for each detector station. These are averages over 5 days. So the amplitude of oscillations didn't change much from stations 1 to 3 because oscillations were not quite developed in this section, and these ramps were lightly used. But then you see this huge growth in amplitude when oscillations propagated from 3 to 5, probably because of lane changing and subsequent car following effect. This growth, however, did not continue. And in fact, it diminished as oscillations propagated from 5 to 6, where this on-ramp is located. By the time oscillations propagated to this section, they were quite developed. They were synchronized across lanes. And the demand for this on-ramp is quite large, so that on-ramp queue persists for long periods of time. You may think that this reduction is quite moderate, but looking at the rate of growth observed downstream, this reduction is actually quite large. So in other words, if I project the growth based on the rate observed from stations 4 to 5, this reduction is actually about 30%. And my theory predicts this % reduction quite accurately. And the theory was verified in more detail at this on-ramp where video was available. So what goes on near a congested merge? It seems that there are two counteracting effects. One is that lane-changing maneuvers induced by ramp inflows cause oscillations to grow. And the other is that on-ramp inflows themselves dampen oscillations. And what we observe is the net of the two effects. And the proposed theory is that apart from the lane-changing and subsequent car-following effects, on-ramp inflows dampen oscillations, and off-ramp outflows amplify them. And when I present the theory, I'm excluding the effect of lane changing and car following. So here is a hypothetical freeway merge with an on-ramp. So here the travel direction is upward, and this section of freeway is queued because of a bottleneck located further downstream. And oscillations that formed near the bottleneck propagate against traffic flow. And by the time they reach this section, they're synchronized across lanes. And I'm further assuming that because of this freeway queue, and large demand to get onto this freeway, the on-ramp is also queued for a long period of time. And this on-ramp is not metered so that the inflows from the on-ramp change in response to the oscillations observed downstream. So the conditions on this freeway is described by this fundamental diagram. Since this freeway section is queued, the condition on the freeway downstream is somewhere on the congested branch, marked as D, and the corresponding flow is Q sub D. And by flow conservation, sum of the inflows from the freeway upstream approach and on-ramp equals the downstream flow Q sub D. And these inflows are determined by the ratio in which drivers take turns at the merge. So for example, if this is a single-lane facility and people take turns on a one-to-one basis, then the merge ratio would be 1. So in another study, I showed that this merge ratio is site-specific, but for each location, this merge ratio is approximately fixed for any queued condition downstream. So based on this merge ratio, U is the state on the freeway upstream, and Q sub U is the corresponding flow. And the vertical difference between the two states is the on-ramp inflow Q by flow conservation. So now let's assume that the flow on the freeway downstream increases by delta D because of oscillations. And vehicles from the on-ramp and freeway upstream approach share this increase in flow in such a way that the merge ratio remains constant, since it's approximately fixed for any condition downstream. So accordingly, on-ramp inflow increases to Q prime, and U prime is the new state on the freeway upstream. And the resulting increase on the freeway upstream is delta U. And since Q prime is larger than Q, delta U is smaller than delta D, indicating that the flow perturbation decreased in magnitude as it propagated past this on-ramp. And some simple derivation will show that the percent reduction is the proportion of on-ramp inflow. So here is the freeway merge that I used to verify this theory. So this is, again, I-80 eastbound. So this section is located about 5 to 6 kilometers upstream of the bottleneck. So this entire section is congested, including the on-ramp. On-ramp queue lasted about 50 minutes to an hour. And vehicle counts were obtained at these 3 measurement locations to measure amplitude of oscillations. So these are deviation curves constructed for the on-ramp and the freeway location immediately downstream of this on-ramp. So the lower deviation curve corresponds to on-ramp, and you see that these deviations were clearly correlated with the deviations observed on the freeway downstream. And this indicates that on-ramp inflow did change in response to the freeway oscillations downstream. And these are root mean squared errors computed for the 3 measurement locations. You see that the amplitude increased as oscillations propagated from x2 to x1, and then it diminished from x1 to x naught, where this on-ramp is located. So to measure the percent reduction of oscillations, I projected the growth from x1 to x naught based on the rate from x2 to x1 to account for the growth due to lane changing and car following. So, and the percent reduction computed based on this projection was 14.3%. And And the percent reduction predicted by the theory was 15.1%. So to compute this, the merge ratio was obtained empirically. And going back to this on-ramp, based on the projection, the percent reduction was 28%. And again, based on the merge ratio obtained empirically, reduction predicted by the theory was 27%. Again, quite close. So you can apply similar logic to off-ramp case, and you will find that off-ramp outflows amplify oscillations. And as I mentioned, I'm in the process of verifying this part of the theory. So to conclude today's presentation, in multi-lane traffic, vehicle lane changing is a primary cause for the formation and growth of oscillations. And car following behavior plays a role that is subordinate to lane changing. This implies that behavior in multi-lane traffic may be different from that in single-lane traffic. And freeway ramp flows affect the growth of oscillations such that on-ramp inflows dampen oscillations. And these are some possible future extensions, which include verifying the effect of off-ramp outflows on the growth of oscillations, and the mechanism for lateral propagation of oscillations to other lanes. I mentioned a couple of times that oscillations became synchronized as they propagated upstream, but there's not enough empirical evidence to show why that happens. And also, it would be interesting to study how oscillations stabilize or decay over space. And finally, it would be interesting to model lane-changing maneuvers. And Laval and Daganzo made some progress in this regard in their multi-lane hybrid traffic model. So quick acknowledgement. I would like to thank my advisor, Professor Mike Cassidy, and Professors Carlos Daganzo and John Rice for their insights and support. And I want to thank Federal Highway Administration, Cambridge Systematics, and Berkeley Highway Laboratory for providing me with such valuable data set. So that concludes my presentation today, and I'll be happy to answer any questions you have. And please make sure you use the microphone. Yeah.
So I guess I'm assuming that ideally that these oscillations are undesirable from an efficiency standpoint.
What do you mean by efficiency? The throughput
Well,
through
just
the bottleneck?
efficiency of movement of people and a bit of traffic flow. I mean, is that a fair assumption?
Well, these are undesirable. I don't know about in terms of efficiency, because when you usually mention efficiency, you are speaking in terms of throughput through the bottleneck. But there's some studies show that these oscillations actually don't really affect the capacity through the bottleneck. So.
Well, I guess I was using that as a lead-in.
Okay.
Are there any, for the lane changing part of your research, are there any policy implications that you've thought about? Or are you aware of things that have been done in other places to discourage people
from lane changing?
Well, but trying to insert themselves in too small of a space. I mean, are there any policy implications for that?
So you are asking me about countermeasure type of thing. So I guess my opinion is that prohibiting lane changing is probably not realistic. But what you can do is I show that car following is involved. So if you want to minimize the effect of, if you want to minimize oscillations, maybe you can play with that car following effect. So for example, people study adaptive cruise control so that way you can minimize oscillations. But there are some possible policies, but I don't know if they are going to be related to lane changing. That's my opinion. Yes?
Kind of along the same lines, have you studied the effects of human behavior in any of your models?
Human behavior. So are you mentioning, for example, like discretionary lane changing versus lane changing because of OD pattern, or?
Yeah, I mean, human behavior in terms of driving, someone sees brake lights, some people decelerate harder than others, some people change lanes in too tight of spaces, just the human behavior aspect of operating
well,
vehicle.
what I did study, what I did study was maybe, like for example, if I need to get off through the off-ramp located quarter mile, then maybe I want to change lanes very quickly. So I may be very aggressive in my behavior. But things like that are very hard to study because I'm not sure if it's going to be feasible to study human behavior. So I'm not really sure how you can do that. But I tried, but didn't really work out. But
I'm just curious on what the lane changing maneuvers were, if they're going left or right. 'Cause I noticed a lot of people go left.
Both. Yeah, I didn't really differentiate the two. Well, actually, I tried to look at the difference between the two, but I didn't really see the correlation.
You mentioned how the oscillations synchronize as they propagate upstream, but I noticed in your correlation plot at one point
It diminished a little bit.
right, and
It's probably because, I don't know if I can go all the way back to that slide, but the reason is there is an on-ramp, and the inflow from that on-ramp is quite large, so that there might be some disturbance created by those incoming vehicles.
would you say, so the correlation you showed was across the lanes, right? So you're
Right.
saying that the on-ramp affects
Right.
maybe the right lane more than
Right,
the
but it did decrease a little bit, but it still was much larger than the correlation that you observe near the bottleneck.
Some of the maps showed an HOV lane on one side. Do you think that had any impact on people's lane changing patterns? Was it like a restricted access HOV lane? Or?
Yeah, I actually didn't look at that because the condition on the HOV lane tends to be different. So basically, I just didn't include the data from the HOV lanes. But what I observed is that I didn't see many lane changing in and out of HOV lanes. So I felt that that was safe to do so.
So you could treat it like a wall.
Yeah. But actually, somebody raised an issue that maybe people trying to get in the HOV lane and trying to get out of the HOV lane, so there might be some sort of effects, but I didn't really study them. But very good point.
Curious, just because this isn't my field, how did you process all that photo, the camera data? I mean, how did you?
Well, I was lucky. Well, that was actually low point of my life.
I was picturing you sitting there watching,
Yeah, that's pretty much how I did it. So for the westbound direction, that's pretty much how I did it. So what I did is, so I marked all the reference points along the freeway. So I used a big big semi-truck, so that I know the length of the semi-truck, so I just marked the location. And then I just recorded arrival times of individual vehicles to the series of reference points. So I did that for the westbound direction because there was no trajectory data available near the bottleneck. But for the eastbound direction, towards the end of my study, Cambridge Systematics and Federal Highway Administration, they did a study so that they obtained half an hour of vehicle trajectories to, I think they did that to study simulation models. But these were called
basically you
NGC.
did sort of process it all by hand. There wasn't any automatic way to
Right.
process it. Okay.
Right. So when I started this study, there was a researcher who was doing image processing and all those things, but it tends to be very challenging and not very accurate. When I joined, the accuracy was about 80%. And to give you a perspective, for the eastbound direction where vehicle trajectories were available to me, they used image processing technique, but they also did it half manually because you cannot detect all the cars from the video. So still, it's like a separate research topic, actually. Yeah?
Just curious, roughly, were you able to determine a particular car and how many times it would change lane or change lanes on that given stretch of field?
Oh, you mean for like one specific car, how many times?
Be able to get information regarding to the event down to one specific car, or how many times?
Well, I studied the OD pattern. So I captured one vehicle, and then I studied how the vehicle ended up later on in space, but I didn't really see anything systematic.
What's the, can you talk a little bit more about the relationship between the oscillations and bottlenecks? Did you look at that at all? Or?
Well, unfortunately, the 8 loop stations, they were all located upstream of the bottleneck. And then I didn't have any data downstream of the bottleneck, so I couldn't really study the relationship between the bottleneck and oscillations. But in a previous study, so they used a Canadian freeway, and then all the loops, the loop detectors contained a bottleneck in between. But what they observed is that so when oscillations form, they propagate upstream, but they don't really propagate downstream. So what they conclude was that these stop-and-go driving, they don't really affect the capacity of the bottleneck. I don't know if that answers your question.
No, that did. I was just, I guess I was thinking also about consistency of speed. I mean, people, I'm guessing on a freeway, they don't like stop-and-go traffic. It's not, it seems like it causes problems, and there's more opportunity for car wrecks and things like that.
Oh, so. In terms of safety?
Yeah.
Well, I think people suspect that oscillations, in terms of safety, oscillations are bad things. But I don't think there is any study that actually show that oscillations worsen safety. But, that remains to be seen.
Do you look at semi-trucks? Because I know those tend to dampen the oscillation. They just continue at a steady speed. Because I always follow a truck when I get in the queue because they don't stop. They hate to stop and go. They just travel.
No, that's a very good point. But no, I didn't. But that would be interesting to see.
Any other questions?
Have you considered how you would apply this into our world? Into the real driving world?
In terms of smoothing oscillations, or?
Yeah.
Well, there are a number of possible options, but it's a little bit complicated. Because, for example, I thought maybe you can use, because the theory suggests that you can use on-ramp inflows to dampen oscillations. So maybe you can do something with ramp metering. But ramp metering has different set of goals. So you kind of have to think about what the consequences are in terms of other measures and so on. Or perhaps you can use VMS sign so that you can tell people that don't follow your lead vehicles too closely. But I don't know how realistic that would be. But there are some possible options, but none of them, I don't think, have been studied at this point.
Any final questions? So before we thank our speaker, I'll just remind you that Friday, April 7th, Steve Garretts from Oregon State University, he's the director of Team Oregon, will be talking about motorcycle safety, an oxymoron with an attitude. So we hope to see you then, and have a great spring break. And thank you, Sue.
Thank you.